So first of all, thank you for Zoltan for the organization of the workshop, and also to Javier Net, of course, and to all of your team for bringing us the opportunity to meet here in Budapest. That's a lovely city I personally didn't knew before. It's amazing. I invite, if you still didn't have time to visit the city center, it's really beautiful. Lovely. Thank you very much. So I'm going to give just a very fast presentation or overview of the WP3 activity because today we are going to focus mainly on the WP3 presentation. So we are going to have a lot of information about the activity that we are developing in the scope of this work package, and also on the future activities of this work package. So I'm going to be really fast because I'm going to talk after the refreshment again about this. So in WP3 we are working on the cloud technology, and as Javier Nieto mentioned it, what we are trying to develop is the connection between the bottom of this slide, the infrastructure layer. We have there the machines, the hardware, and so on, and the top of this slide, that is the developers and also the final users. So we need, what we have found is that we need to work hard on the connection between the developers and the software that you are developing to be able to move this software fast to the hardware. So you can take the opportunity to scale your software in fast supercomputers, but also on the cloud very fast. So we're mainly working on the infrastructure layer, providing the cloud technology, also working in the monitoring, not only on the monitoring of the infrastructure, but also on the monitoring of the applications to provide useful information to the final users about how the simulations are going on, if the application is running good, if it is producing really good results, or if something is failing. Then we have our orchestrator, that is a piece of software that will be able to complete all the steps in the simulation process, including pre-processing of the data, the simulation, and also the post-processing of the data. It's like a kind of workflow manager. And then we will be also developing a portal in which not only for the users to submit the simulations to the infrastructure, but we will integrate other tools in this portal that will be very useful. In principle, for example, for the software developers to publish new versions of the software that you are developing, to make them available faster to the final users, and to the users to select the different software that they want to use directly from the portal, and to use this software directly also in the available infrastructures. Right now we are providing a supercomputer to the project, that is the finished array, but we are also using a cluster from STA for testing of the technologies, and we will be incorporating an Atos infrastructure in the project. But the aim and the scope of the project is to incorporate new infrastructures so they can be easily used for the software using this the cloud technology that we are developing. Very easily to incorporate your own resources. For example, if you have some local cluster in your premises, to use this local cluster, but also in connection with other European infrastructure, like for example the Porous infrastructures or the EGI infrastructures in Europe. I will not talk more about the activities of WP3 because we are going to have whole sessions during the day. So that's all from my part. Thank you.
Hello, I'm Christophe Prud'homme. I'm a professor at the University of Strasbourg in applied mathematics, and I'm in charge of WP4. This is the work package for the mathematical frameworks. That is Phoenix, OPM, and Fil++. So basically the underlying workhorse of the pilot application that we are going to run in the project. So the objective here is to be able to define the different specifications that would be required of the mathematical framework in order to run in the cloud. But we'll see later today how it is designed, I mean the cloud framework, and we'll then develop the various changes in the mathematical framework in order to run this. But however, I will discuss a little bit some aspect of the change that might be required or not, because I think the three frameworks have already a lot of ingredients in them in terms of architecture, usability, packaging, and deployment. But I would like to mention something which is a big trend in scientific computing, at least, or for many software actually, but type of software. You want your scientific software to be automated, as much automated as possible. You want it to be scalable. You want it to be integrable. You want it to be capable. What does it mean, capable? It means that you want to be able to do all different kind of operation. Like you don't only want to solve a problem like fluid flow, but you want also to optimize, to be able to optimize in an automated way, or rather automated way, the flow around some objects or around a structure, like an airplane, for example. You would like to incorporate advanced analysis, for example, in your software. So you want to integrate new features that help engineers, researchers to make the right decision. Integrable, what does it mean? It means now, as actually Zoltan showed, in the simulation system, you have a large set of tools with a chain that is actually run. So you need your different pieces, and often which are requiring large simulation, to be linked together and integrated into another piece of software. So your software needs to be flexible enough to be integrated in complex chains. I will mention tomorrow, for example, a pipeline that we develop in medical science, and where we are integrating various software in a rather complex chain. And scalable, of course, because you want to be able to take advantage of high-performance computing. So we want this, definitely. So here we talk about these three mathematical frameworks. This is what we are going to develop, and they are the basis of different application that will be run within the pilots. So what is, I'm going to make some teaser slides for the different mathematical framework. They will be shown tomorrow and on Wednesday. So Fil++, so we develop Fil++ in Strasbourg mainly, but we have also various partners and collaborators for this development. So it's a C++ mathematical framework that allows for a large set of Galerkin methods from finite element, spectral element, or reduced basis methods. It supports an advanced language, so mathematical, basically to write your mathematical formulation within C++ to ease the programming. And it scales on a large number of processors. It uses well-known frameworks like PET-C and SLEP-C, but we develop also homemade preconditioners for very large-scale problems where we can actually sometimes be actually better than those guys in some situations. And in order to automate as much as possible, we provide toolboxes which are allowed to easily set up mono or multi-physics applications, and to create new ones, thanks to the mathematical language, it's easy to add a new toolbox. And lastly, we have also, and that could be interesting for MSO4SC, I think for the discussion, because we have also enabled reduced order methods, which allows for real-time simulation. That is, you have your very large simulation, which is parameterized, and you would like to reduce the number of degrees of freedom. So we have methodologies for that. And then the solve time would be like in orders of magnitude smaller than with the initial system, like say in finite element. So that could be also interesting to look at this as a next step eventually for MSO4SC to integrate in this framework. So this will be discussed on Wednesday. Regarding Phoenix, so Phoenix is all about automation. It also provides, like in Fil++, the language for developing nicely, very close to the mathematics, or like the mathematics, say, your problem. And based on, say, the variational formulation, you have automatic generation of the software. Also the mesh, this is from what I understood from what Johan sent me. So, because here, what you see here is actually a mesh which is generated automatically from the problem definition, and I think here is after a few adaptations. So it will be presented on Wednesday, and you will see how they can produce this kind of simulation from rather nice definition of the problem. Very nice definition of the problem. They include also automated optimization, which is an extremely powerful framework in order to actually do this kind of simulation. And of course, they scale. If we want to present, OPM is about flows in porous media. So basically, it's not basic actually, it's flow in a reservoir simulation. It provides various toolbox in order to tackle a wide range of simulation. And you have access here to various benchmark data, and it seems full cases. But I'm sure Edgear will present that on tomorrow in detail, what will be available. And they have, so this is, I guess, the REST Insight software in order to do the visualization of the porous media flows. So if I go back now to the different thematic, to the different aspect of the work package, in terms of software architecture, what do we want? We want a building process which is rather standard. I think all our framework follows the same process, which is good. We use all MPI. Maybe some of us also are also multi-threaded, allow multi-threads within MPI. We use tools, or we share some of pre-processing tools, like, for example, with Phoenix or with Fil++ Salome, which is software developed in France for to do the full simulation chain from pre-processing to post-processing. Gmesh, of course. And regarding post-processing, I don't know if REST Insight is based on ParaView, or this is Insight, or this is your own software. This is your own software.
It's open source.
It's open source software, okay. But ParaView is also used by Fil++ and Phoenix, so we share this. And within the project, we'll have also ParaView Web, the web interface for ParaView in order to visualize our results. There are also some in situ capabilities. Actually, it should be here in co-processing with ParaView, which allows to interact with the simulation directly. So actually, we share a lot of things between the various frameworks, I think. There are, of course, differences. And some of the major developments will be probably in the monitoring and of our framework, so that the cloud people can actually understand what is going on, and either in terms of performance, debugging, or just interact with the simulation, perhaps. In terms of usability, documentation will be an important point. The mathematical frameworks eventually have their own documentation set, but we propose also to have some tools in order to generate nice technical documentation from the specification that we develop here. So for example, we set up, so this is the current address. I hope it will become book MSO4SC.eu, but I'm sure it will be done soon. So this is a recent discussion about being able to deploy easily technical discussion on a website directly. So for the deliverables, but also the specs, some codes, some examples, benchmark specifications, things like that. You can access this. There are other examples of this kind of technology. We use it for Fil++. If you look at book.filpp.org, you will see what we have done with this. There is another aspect here in order to be able to go to not only to provide pilots or simple modification of simple or just parameterization of the pilots. We would like to be able to allow the user to develop new applications. And here scriptability plays an important role. Phoenix definitely has this capability. For OPM and Fil++, this is not so the case. However, there is a nice project at CERN, which is a Kling interpreter. It's basically a C++ interpreter. So you take your C++ code, and this is interpreted by Kling. So you have scripting capabilities for free using Kling. However, there are some performance issues that needs to be tackled. And there will be, of course, access to shared scripting if we cannot have scripting a la Python or using Kling. Packaging. We have been working a lot on packaging. Each framework will be able to present their achievements on this, but regarding standard Linux packages, I think it's helpful to have those because it's easy for users or external users to be able to access the software. I don't know the stage at which all the frameworks are in this area, but we can probably discuss that tomorrow and on Wednesday. And there is this container system, container technology, which is very nice to be able to deploy applications. So initially we started with Docker. However, there are some issues, like if you want to deploy Docker on a cluster, usually the engineers are not happy regarding the security. And so we move also towards the solution of Singularity, which is developed at Lawrence Livermore, and which provide a nice secure environment for the clusters. And also as shown in benchmarks that actually Docker also provides very nice performance, and Docker and Singularity provides extremely nice performance with respect to parallel computing. So, and the idea is that we want to be able to run application in a very simply. So the first command, this is just an example. I'm not saying like it will be exactly like that, but basically here, thanks to Docker, for example, you can just retrieve the software with this command, the Docker pull, and Docker run. You just run. Well, it's a tad more complicated than that, but it boils down to this in order to run the applications. So it should be as easy as possible to run the pilots and the applications. This is an example of what we have done in Fil++. So we store on Docker Cloud. This is a free, there is a free repository here where you can upload your Docker images, and you have access here to various Docker images. If you are interested, you can also pay for private repositories if you don't want to expose some of your work. This is extremely powerful framework. And the last part is about deployment. So in that case, that would be through MSO4SC. Docker Cloud, actually, that I just shown you a screenshot of the Docker Cloud web page. Docker allows to deploy services. They have here, you see, they have all kind of tools to deploy services, but not necessarily to do high-performance computing or to deploy big applications. So here we are going to use the MSO4SC infrastructure, and Javier Camero will present the entire pipeline, which should look like this, with 4 main stages where you start here from the MSO portal to the deployment on the compute nodes, running the simulation, making sure that everything is all right, and then visualization here. So that's what we are going to discuss this afternoon, right? Well, there is the last bit. This is like, you know, the mandatory deliverables. So we have to deliver one soon, actually, on the mathematical framework, following the discussions on WP2 and WP3 regarding the infrastructure. What does it mean for our mathematical frameworks? What we need to do? So we need to deliver this very soon. But I think in general, we are looking good in terms of what we provide so far in terms of build and runtime environments. And then, and the second stage, we'll need to provide where we stand regarding the implementation of what we did. So thank you for your attention, and that's it.
Okay, so my name is Johan Hoffman, and I'm the work package lead for work package 5. And that is about the pilots or the end user applications. So first, the objectives is then to demonstrate and showcase the capability of this infrastructure. And that will be done in terms of a set of pilots. Most of them build on one of the 3 mathematical development frameworks, and then there are a few pilots outside that. And this work package is about first defining these pilots, and then to provision the infrastructure needed, and then implement the pilots. And this will be done in 2 iterations. So the deliverables represent 2 such cycles. So first defining and defining the pilots, and also an evaluation strategy. Then to bring about infrastructure, basically integrating the results of work package 2 and work package 3, and then implement the pilots on top of that. And then we end each cycle with an evaluation report. And this is the protocol that we will follow, which is based on verifying the needs identified in work package 2. And we will do this in 2 steps. The first one verifying a TRL level of 7, and then a TRL level 8. And basically the difference is that on TRL level 8, the end user should be able to run these pilots on their own. So all these pilots will have dedicated time during Tuesday and Wednesday, so I will not go into too much detail, but I will show a teaser of the different pilots. So as mentioned, there are 4 different groups. There are the Phoenix pilots, the Field++ pilots, the OPM, and then 2 pilots which are outside this. Also, there are already being indications of additional pilots to be added. That will be also discussed on Tuesday and Wednesday. So, starting with one of the Phoenix pilots, the floating wind turbine. Here, the context is the design of floating wind turbines with the focus on the floating platforms. So the pilot will function as a design tool for virtual design of such platforms. And for each pilot, we also define test cases. And test cases will function in this first iteration of the pilots as an evaluation criterion to verify that the pilot is performing the way we expect. So in this case, there are 2 test cases. One is derived from the Nautilus platform, which is an established benchmark where we have experimental results. And then one general basic benchmark called the marine benchmark, which is used in the scientific community, where the focus is the free surface flow. Another Phoenix pilot is the CFD-Dispersion, and this will also function as a subroutine for the 3D air pollution or air quality prediction pilot. Basically, this is a computational fluid dynamics pilot together with the dispersion module. And to evaluate the performance of this pilot, we have chosen an urban street canyon problem. This is identified here as this is the 42nd Street in New York, and to the right you see a model version of that, which there are detailed controlled experiments that we can use to verify this pilot. Moving on to the Field++ pilot, we have the hi-fi magnet. And the context of this is that this is used to develop the existing and to design the next generation of high field magnets. And this is in particular in a collaboration with the LNCMI. And this is a multi-physics problem, and one of the main demands is the actual coupling of the multi-physics. And that becomes even more elaborate in the I2 Brain pilot, another Field++ pilot, where also data is integrated from various modalities. And the goal is here to model the function of the eye, certain functions of the human eye, with the purpose to draw conclusions of brain functions or early indicators to detect neurodegenerative diseases. The OPM Flow application is dedicated to model very complex porous media flow, where with realistic geometries and including also different wells and the connection of these. And this is also a very complex coupled problem, including some specific features like automatic differentiation, which distinguish this from the other pilots. SIB Affinity is a pilot with focus on the pharmaceutical companies. So the goal is to be able to predict likelihoods of bindings of potential drug molecules. And finally, as was described by Zoltan before, is the 3D air quality prediction pilot. And here the goal is to connect models of the traffic, which then function as an emission source in an urban environment, and based on meteorological data, solve the computational fluid dynamics problem and draw conclusions about various hotspots of pollution. And this could be used both as a monitoring or forecasting system, but also potentially as an urban planning tool. So that's the basic set of pilots that we defined in the proposal, and which we will use in the first round of verification for the project. Thank you.